So far we have learned a lot about functional dependencies. And now we're moving into the second part of the chapter, and perhaps the more important one, which is that given a relation with a set of functional dependencies, is it a good relation? In other words, what makes for a good relation? What makes for a good set of relations? And if I don't have good relations, then can I derive them from the ones that they're not good? And that's the purpose of the second half of the chapter. How do I design good databases? And which implies how do I design good relations? Let's look at the example from the notes. It's the same example as in the book, section 3.3. And so we have our movies relation. We have title, year, length, genre, studio name, and star name. And we only have one functional dependency. Title, year implies length, studio, and studio name. If you're a little bit observant, you will probably realize that the primary key of this relation is the title, the year, and the star name. Okay, so those three attributes create the primary key of this relation, or the candidate key, because we only have one candidate key. And in fact, we could write it as another functional dependency here, but that will be redundant. This will be the minimal basis of this relation. So the fundamental problem with some tables, with some relations, is that they have redundant information. And this redundant information brings some interesting problems that we want to try to minimize. We might not be able to avoid them always, but we want to minimize them so their impact is somehow attenuated. So let's say, for example, that I want to update the length of the movie Star Wars. Let's assume that instead of 124 minutes is 125. So one of the problems I have is that I will have to modify it in 3 different places. And if I make a mistake, and let's assume that I only modify it in one place, and I make it 125, let's put it with red, then my information, the information in my relation, is now inconsistent. I have 2 different lengths for the same movie. So I have to make sure that if I modify it in one, I have to modify it in all. This is what we call an update anomaly. An update requires to modify more than one location, and if we make a mistake and we forget one of them, we have inconsistencies. Now, another potential problem is, let's assume that I want to delete all my stars, all the stars that appear in this movie. I want to remove Carrie Fisher, I want to remove Mark Hamill, and want to remove Harrison Ford, for whatever reason. If I do that, I remove these 3 tuples. I have not only lost information about the stars that participated in my movie, but I have also lost the length of the movie. I no longer have it. I have also lost the genre of the movie. And I have also lost the studio of the movie. You can say, well, you could have other stars. Well, let's assume I don't have any star. I have not inserted any stars into my, any stars for this movie into my relation. We will not have that information. You can say, well, you can create a dummy record for maybe the empty string for the star name. Yeah, we can do that. And but that doesn't actually alleviate the problem. It actually means that now we have to deal with the fact that we need to insert every time one dummy record to make sure that we always have the length and the genre. So that's what we called a delete anomaly. And then we also have an insert anomaly. And an insert anomaly is kind of similar to the update anomaly. It's like if we insert, we need to make sure that we insert the length, the genre, and the studio name consistent for the new star name. Okay, because if we do it incorrectly, let's assume that I want to add another person who is a star name to the movie. I have to make sure that it's 125, is science fiction, and is Fox. So that also creates the potential problem of having an anomaly during the insert. So what would be the anomaly? That I insert an incorrect record that is inconsistent with the rest of the data. So those are the problems that we are trying to avoid. So how do we do that? Well, the fundamental principle is the following. If I have a relation with many attributes, A1 all the way to AN, I might want to split it into two relations. B1 to BM, and let's call this S, and let's call this T, and this one will have C1 all the way to CK. Each one of these relations could be 2 attributes, 3 attributes. Well, this one will R will have probably 3 or more attributes. S can have 2 attributes or more. T could have 2 or more attributes. In theory, we could have a relation with 1 attribute, but do we need to decompose a relation of 1 attribute? No. So this is what we call decomposition. We can split the relation R into 2 relations, R and T. Okay? Such that, and these are actually very important properties, B1 to BM union C1 to CK should be equal to A1 to AM. In other words, the attributes, the union of the attributes of S with the attributes of T should give me all the attributes of the original relation. Okay? So that's the first step. The second step is that this relation will have a set of functional dependencies. Let's call them the functional dependencies of R. If we compute a projection, if we split the relation, if we split the relation into S, this will be F. This will have a set of functional dependencies, and this relation will have a set of functional dependencies. F of T. What are the functional dependencies of S? Well, they will be derived from the functional dependencies of R. We will see how that is done. What about the functional dependencies of T? Well, they will also be derived from the functional dependencies of R. But the important property that they must have is that the union of the functional dependencies of S with the functional dependencies of T, the closure has to be equivalent to the set of functional dependencies of R. In other words, once I split my relation, the functional dependencies of the 2 new relations have to be equivalent to the original functional dependencies. I should not create new knowledge, and I should not lose knowledge. Okay? So this is what we call a good decomposition. Sorry, there's one more rule before we go into good decomposition. There's one more rule that that they should have. So this is number 1, this is number 2, and I'm going to write number 3 here. And that is that if I combine the relations S and T, they should give me the original relation. We haven't seen this operator. This operator is called join. If I join the two relations, they should give me the original relation. That kind of makes sense, right? So if I decompose the data into two different tables, into two different relations, when I combine this information together, I should be able to get exactly the same relation that I had. Okay? We call this property lossless join. And we call this property FD preserving. So now I can actually talk about a good decomposition. So what is a good decomposition? A good decomposition is such that it's FD preserving. So the functional dependencies of the decomposition are equivalent, the union of the functional dependencies of the decomposition are equivalent to the original functional dependencies. And it's lossless join. When I combine the two tables together via the join operator, they should give me the original table. Okay. We will see that for the purpose of this chapter, we don't need to understand join. We just need to know that that's a property that is desirable. Okay. But we will be able to understand and determine whether a decomposition is FD preserving. Okay. But that'll come later. So let me just recapitulate. A good decomposition is such that it's FD preserving and is lossless join. Okay. Let's revisit the example that we had before. The Star Wars example. So the original relation with our five attributes, we can divide it into a relation S that has title, year, length, genre, and student name. And in this case, this will be the primary key. And a relation T such that this is its primary key. This T doesn't have any set of functional dependencies. S will have this functional dependency. At this moment, you will have to trust me when I say that if we join these two tables together, if I do S join T, this will be equal to R. So this is lossless join. And it should be obvious, if I union this, and I compute their closure, is equivalent to the closure of this. So it's FD preserving. I only have one FD, so as you can see here, it's preserved in one of them. So this is a good decomposition. It's FD preserving and it's lossless join. Notice we still don't know how to do it. What I really want to emphasize is that when we decompose relations, our goal is to have relations that the decomposed relations are a good decomposition, lossless join, and FD preserving. Okay, let me leave it at that, and then we'll continue in the next video.